Alright class, today we're going to learn about what inverses are and finding them. Basically, you guys learned earlier and also in Algebra 1 that a function is a relation for which every input has exactly one output. And all an inverse does is flip that around on you. So a relation that maps the output of a function back to its original input. Okay? So, for this problem, it tells you that we're inputting a 1, we get out a 5. If we put in a 2, we get a 7, and we put a 3 in, we get a 9. So my domain are your inputs, and your range are your outputs. And then the inverse of that is, if we have the input now as the old output, that'll get us back to an output of 1. That 7 now goes back to 2, and that 9 now goes back to 3. So the domain of the inverse is 5, 7, 9, and the range of that inverse is 1, 2, 3. Notice how these are the same and these are the same. That works when they're one-to-one functions, which means that they are both functions. Alright, what it means symmetrically. You're reflecting over the line, and actually I wrote, that was what I was going to write here actually, hold on. Domain of the function equals the range, and then the range equals the domain. We're lagging a little bit today. Okay, and then it's symmetric over the line y equals x because you're switching the x and y. So here's the line y equals x. So that means all the points for an inverse reflect over this line. That was a terrible line. There we go. Alright, so for example, if we take these points, I'll do the function in blue. So 1, 5, 2, 7, and then 3, 9. And then I do the other one, the inverse in green, 5, 1, 7, 2, 9, 3. You can see that these points have flipped over this line y equals x. To write the equation of the inverse, there's two steps. Switch the x and y coordinates, and remember, y is the same thing as f of x. And then solve for y. When you're done, if it was given in function notation, the notation we use is f inverse of x. This does not mean we're flipping it down. Okay, this is just a notation thing. So when you see that, that just means we found the inverse of f. So let's do these. Switch the x and y. Remember, this is the y, and then this is the x. So this is going to now be your x. This is going to now be your y. And now resolve for y. So I'm going to add 5. And I'm going to divide by 3. So you get y is equal to x plus 5 all over 3. And again, the final answer though should be in function notation. So this was the function. We just found the inverse of the function. So that's our final answer. Let's do it again. This was our y, so it's going to be our x now. And our x turns into y. We subtract 6. Divide the whole thing by -3, and we can say f inverse of x equals x minus 6 over -3. Okay. To verify that something is an inverse, you have to use composite functions that we were doing the last 2 days. If you do f of g of x and you get x, and if you do g of f of x and get x, they are inverses. Okay? So let's do f of g of x first. F of g of x, which means I'm taking g and putting it into the f equation. So I get 1/3, and then the g equation is 3x plus 3. And guys, with these, it's like a proof. I'm not grading the final answer. You should know that you're going to get x. Okay? I'm grading your algebraic steps because sometimes people make mistakes, especially on things like number 4. We'll get to that in a second. So the first step that I can do here is I can distribute this 1/3. 1/3 times 3x is x. 1/3 times 3 is plus 1. And then we still have that minus 1. And sure enough, when you add those two like terms together, you're just left with x. Let's do it in the reverse. And I have 3 is g of x, and we're putting in a 1/3 x minus 1, and then we have a plus 3. Alright, so we multiply the 3 in first, because that's all we can do. 3 times 1/3 is an x, 3 times a negative 1 is a negative 3, and then we have a plus 3. And sure enough, we get x. Okay, so we just verified. So these two things are inverses. These two functions up here, f and g, are both inverses of each other. Okay, let's do it again. Again, be careful with your algebra. F is this one here. We're putting g in there. So where x was, we're going to put a parentheses. We have the 5th root of 7x minus 2, all to the 5th power, plus 2, all over 7. Alright, the first thing you notice, hopefully, is that the 5 and the 5th root cancel. So we're left with 7x minus 2 plus 2 all over 7. Don't just say x at this point, okay? We can't cancel that out until we've gotten rid of the like terms on top. Negative 2 plus 2 is 0, so I get 7x over 7, which now is x. Please show that step. G of f of x. We have the 5th root of 7 times this whole thing okay? So, first thing you can do is simplify the inside because we can't take the 5th root yet. There's a minus sign. Remember, you can't take roots with plus or minuses in here. So we'll have to just work in the middle here first. 7 times this fraction, the 7's cancel, and we end up with just an x to the 5th plus 2 minus 2. Again, don't just say, oh, I'm 5th rooting all of them and then subtracting. You can't do that. You have to subtract first, and I'm left with just x to the 5th because those go away, become 0, and finally I get x. So again, they are inverses. Okay. So in this case, we know the vertical line test tells us that the relation is a function or not. You use that whenever you see a graph, okay, and that tells you if that graph is a function. A horizontal line test you use on that same original graph to tell you if its inverse is a function, so you don't have to graph the inverse. It's really a way to not graph the inverse for the horizontal. So let's graph 2x plus 1. It starts at plus 1 and has a slope of 2. Okay. First thing I'm going to check is this a function? So what I would use is, this is the original, I would use the vertical line test on this. And sure enough, it only hits it at one spot each time you draw a vertical line. So we would say that f of x equals 2x plus 1 is a function because it passes the vertical line test. Don't tell me it is a function because it passes the vertical line test. I need to know which function you're talking about. This one is a function because it passes the vertical line test. This one, we have a horizontal line test now on the same function. Since every horizontal line only hits once, that means that the inverse of this line will also be a function. So the way we'd write that is the inverse of the function is also a function because the original, you have to say that. You can't just say because it, because if you say it, you're implying the inverse did. So it's because the original passes the horizontal line test, the original function. Okay? So you use the horizontal line test on the original. Or you could graph the inverse and then do the vertical line test on it to see if it's a function. All right, let's look at a couple of these. Does the relation have an inverse? Yeah, we can rearrange these points and flip this thing over that line. Yes, it does. We can map all the points to something else. Is it a function, though? Well, if we want to know if the inverse of this is a function, we can just do a horizontal line test. And clearly, no, because the function, not the inverse, fails the horizontal line test. Okay. So again, the blue graph is a function because it passes a vertical line test, but its inverse is not because the blue one does not pass the horizontal. So let's graph f of x equals x squared, our basic graph, 0, 0, 1, 1, negative 1, 1, 2, 4, 3, 9. Negative 2, 4, negative 3, 9. All right. So there is that. And I'm going to also, first of all, is that a function? Yes, because it passes, because f of x equals x squared passes the vertical line test, right? So before doing the horizontal line test, we're going to graph the inverse. And here's how you do that. I'm going to map out all these points. So I'm going to do an XY chart real quick of everything I did. So I had negative 3 gave me 9, negative 2 gave me 4, negative 1 gave me 1, 0, 0. You can get these from your table if you need to. So that's the original, right? So the inverse is if I switch them. So for the inverse, the inputs and the outputs are switched. So I now have 9, negative 3, 4, negative 2, 1, negative 1, 0, 0, and the same thing, 1, 1, 4, 2, and 9, 3. So if I graph those points, I do 9, and then at negative 3 and positive 3, there's a point at 9. At 4, there's a point at negative 2 and positive 2. At 1, there's a point at negative 1 and 1, and then we have the vertex. So this is the inverse of that original function. So we graphed it. Is the inverse a function? Now there's two ways you can tell me why it is. You could either say no, it's not, because the inverse, the thing we just graphed, fails the vertical line test. Remember, the vertical line test tells you if that thing itself is a function. Or you can say no, because the original, the green one, fails the horizontal line test. Either one works. Okay? Well, since we just graphed these, we can also answer this question. The domain and range for f of x and f inverse is x squared right now has a domain of all real numbers. And the range is that the y values have to be greater than or equal to 0. If you look at what we graphed in blue up here, now the x's start at 0 and only go to the right. So the domain are the x values such that x is greater than or equal to 0, and the range, or the y values, go both up and down, so we would say that. Okay? How can we limit f of x so that both of those are functions? So basically we're saying, if I wanted to make that, what would I say f of x only is? Well, basically, if you look at this, the reason why this is not a function, the inverse is not a function, is you have two parts of it. So if we only have one part of it, for example, when x is greater than 0, then we're only going to have this piece here. which will make it a function. So we can limit it by stating the original domain at the original is x is greater than or equal to 0. Because then that gives us, so the domain is greater than or equal to 0. That gives us just one piece, which will pass the horizontal line test. And when you graph it, that piece will then pass the vertical line test. So, okay, so big thing though, inverses right now. The x and y switch, solve for y. And verifying, just be careful with your algebraic steps. And then remember your tests. Vertical is always done on the thing that's there to know if that thing is a function. Horizontal is done on that on a graph to see if its inverse is a function. Okay, good job.